Good afternoon, everyone. I'm Barbara, and I will be talking to you today about machine learning with R. So yeah, I encourage you to put on those headphones. Out of curiosity, who has ever worked with machine learning here? Oh, that's really exciting. Much more than I usually get. Who came here to hear about this hype thing, machine learning, AI stuff? You know what? You're a minority. First time I give the talk like this, and this is the ratio. Okay, so who am I to talk to you today about machine learning with R? I'm ex-Microsoft, and at the moment I'm a data science freelancer. If you're wondering what it is, it's kind of a new thing. I think I kind of made it up. If you want to know what it is, talk to me later after the talk. My background is in machine learning, but I also have been a programmer, software developer for more than 12 years. So I have a strong programming background. All what I will be showing you today is on GitHub, and I also am now a content creator on machine learning and AI on a platform that's called Categorical, and all this code with all the demos, it will be there for you to use, so feel free to look at this later when I actually put it, but so far I've created some other courses. If you're interested, just look at this content. Feel free to tweet me, feel free to email me if you have any questions. I'm pretty good at responding, so don't be shy, keep in touch. So what's the agenda for today? Very simple. I will give you an introduction to machine learning, and then a little bit about our platform, and then we'll go through 3 exercises for 3 classical machine learning tasks: classification, regression, and clustering problems. So what's machine learning? Who will tell me what's machine learning? I will repeat if you can tell me. Who can tell me what machine learning is? I'll just stop right here if you're... No microphone. I will repeat what they are saying. Come on. You, sir. No? Okay. You are a shy audience. So the answers I usually get is robots, AI. That's why I've put the robot there, right? So the perception of what machine learning is kind of like magical. You have a lot of data, you have a lot of information, you put it into this magic box, and it will come back with some answers, with some insight, not just about data, but also about the future, about humankind, about the sense of life. So this is what I usually get if I talk to people. And it is kind of true, but kind of isn't, because it's much more down to earth. So I will show you what, in my opinion, machine learning is on the example I found in one of the books that was written on machine learning. By the way, I think it's a very bad example, but I took it on purpose to show you that it's nothing magical, something that computers are doing all the time. So we have a list of movies. And someone went through the effort to watch all of those movies and counted how many times people kissed and how many times the people kicked other people, or there was some action figure. So then they went through all those numbers, and they also labeled it. So we can see that the genre is there either action or romance. So this is like a classical setting for the machine learning problem, which is called classification. We have a bunch of data and we want to classify, which means assign our records to some category, right? To some label. So let's say we got a new data and someone asks you, let's imagine you are a machine learning algorithm, and asks you what Gone with the Wind genre is. Action? Raise of hands. Who thinks it's action? Romance? Yes, it's romance. And the thing is, the way you came up with this genre thing is either you watched the movie and you have some kind of an emotional binding with it, or you heard about the movie or you heard some kind of quotations and you have already idea in your head. You made this classification years ago, even before I asked this question, and you didn't even look at the data, right? Those kisses and kicks didn't really matter because you're not a machine, you're a human being, and you think a little bit differently. How do a machine do it? Machines are looking at data. So for the machine, the title of the movie does not produce any kind of an opinion, right? Instead of titles, it has some kind of an IDs. Instead of calling the feature kicks and kisses, there is a feature 1 and there is a feature 2. So we have feature 1, feature 2. We have class A and B. Again, no emotional attachments, just A and B. Doesn't mean anything. So I have the question, which class, A and B, will you classify the new record? The new record has the feature 1 of 31 and feature 1 of 4. So is it a class A or is it a class B? You're very shy. It's class B. And you probably didn't raise your hand because you just you prefer to listen to me rather than to raise your hand. So how did we came up now once we have numbers with this class? So we looked at the feature 1 is kind of high, right? And feature 2 is low, so it kind of looks like we found a pattern in this data. And yeah, that's actually how machines are doing. It's just we do it very seamlessly, right? We look, we found, we visualize, we do some stuff, and it is magic, right? Kind of a magic. How machines are doing it is by calculating. All good calculating, because machines, despite what the media are telling you, cannot think yet. What they can do, they can count very, very well. So this was an easy task for us human beings. What if we have, instead of 5, what if we have 500 or 5,000 or 5 million of movies, of records? How would we approach something like this? So one of the ways we could do it is by trying to visualize it, plot it, and see those patterns, because we see. Usually human beings are very visuals. So if you visualize it and like say, oh, those are my dots that represent my data and they're all labeled by A, and those are my dots labeled by B, maybe I can find the line that separates it. And again, this is how machine learning algorithms are making this distinction. And getting another dot, let's say there will be another dot right here, we would think, oh, this is a dot of a class B because it's on the right side of class B. The thing is, with machines and human beings, again, is we told the computer to find the line. The computer didn't come up with the concept of the line, right? We said, this is the line. It has roughly this kind of an equation. Find me the coefficients of this line based on how my classes are placed there, how my dots are there. And actually, computer wouldn't even think of a line. It would think of numbers. And this is why human beings are quite important in this whole process. Because, you know, I just visualized it and I said, well, we can separate those classes. What if we cannot separate it by a simple line? What if we need something much more complex? What if the line is not the proper model? That's why machine learning algorithms still need human beings. We are not so easily replaced, at least yet, so don't worry. Another way we would say, well, find this rule system or find some kind of a decision tree. But again, it's us human beings who are telling those computers to do some stuff, and then those computers are calculating it based on data. So this is machine learning according to me. And this is something that is happening in our brains. So there is an occupation, quite lucrative. In London, you can get 40K per year doing chick sexing. Who has ever heard of chick sexing? By the way, I'm not breaking any code of conduct. This is actual job. Like, Google it. Chicks, when they are born, they are not showing any ways of person, human being, distinguishing between their genders. But because it's very important in the industry, because the gender actually predicts the fate. If you're a boy and you're a girl, you do different things in the chick industry. But apparently, nobody can explain to another human being how to distinguish the genders. But there are some people who can distinguish. So it's like they know how to do it, but they cannot explain it to another person. So what they are doing is they're setting up the colleges, the actual learning courses. So you're sitting next to, if you want to learn, you're sitting next to the teacher who knows, and try to guess. I read something, and they are like touching it or something. I really don't want to know more details, but they're trying to guess. So while this person that is learning is guessing, the person that knows, the teacher, is correcting them and saying, well, you're right, you're wrong, you're wrong, you're right, you're wrong. And apparently after a few weeks, the brain of the human rewires. And after a few weeks, this student can distinguish the gender. The similar thing was with recognizing the aircraft during Second World War. When there is a plane in the sky, you can barely recognize if this is, well, Allies' plane or the Nazis' plane in the Second World War. So there were people who just could, and like governments, many countries were just hiring those people to teach others, so others could spot it, they could go to shelters, etc., etc. So it was much more like a big a process for the people to handle the situation of the aircraft. So what I was telling you, the classification problem, is a part of something that is called supervised learning. Same was with chick sexing. There is a person, there are data that know the right answers. There is a column with labels, with categories. So classification is a typical example of supervised learning. Another one is regression problem. And supervised learning is actually a problem that was very, very difficult till recently in AI, which allowed us to distinguish between cats and dogs. That was the most demanding AI problem for computer vision for a very, very long time. Another problem, another like class of problems in machine learning is the unsupervised learning. And it actually aggregates a whole bunch of different things that cannot be categorized as supervised learning. But the most canonical example is clustering. So if you think of like target marketing, you don't want to put your ads that are personalized to exactly you, because you would need to create so many ads and so many configurations. Instead, companies like Facebook, like Google, they are creating clusters of users that are similar. And we'll go to this. This type of machine learning is considered much cooler because this is this actual like looking at data and finding patterns, and some very cool stuff can reveal. But it's also much harder to judge if you're actually doing a good job, because if you don't know right answers, if you don't have labels, how well can you say your algorithm is doing? There are some statistical models that can give you some metrics, but still those metrics are on how data is shaped rather than how good your algorithm is. Once we have machine learning model, what we want to do is to publish our model. So the training phase, the actual machine learning training phase, is something that is happening, I would say like offline. So you have a lot of data, you train it, and then you publish it, and then you have this thing to predict new ones. So if we had something that can predict the genre of our movies, we would need to like publish it somewhere, like as an API. You've probably heard about some cognitive services, IBM, Watson, and Google services that you can just like upload a photo, right? And it will recognize objects on this photo. This is the exact what publishing the model is. So model is ready to use there and publish for other people to just hit the run button. And now we are starting about R. Who recognizes the episode of Big Bang Theory? So I love this episode because this is the feeling I had. Their final question, they got some things that no one of them knew what it was. And they said, this is something that they dropped on Roswell, right? The aliens dropped it. So that's how I felt with R language at first. And I did some research, and apparently this is the thing with, if you're a programmer, if you're a computer programmer, this is the feeling that you can get with R. Because R was created by statisticians, for mathematicians, not by programmers. If your background is in statistics and mathematics, and apparently in business, if you're a business person, like product person, you find R very easy to read and like, yeah, very, very easy to use. So R was created by two gentlemen, Mr. Ross Ihaka and Robert Gentleman. One of the theories is that's why it's called R, from the first letter of their names. Another theory is there was a statistical language S that was invented in Bell Labs, so they did the open source version, called them R. It's very community driven, so I would say it's a blessing and a curse. So you have a lot of people working on R, and I know there is this war if Python or R is better. I just think you should choose your tool for the specific job, and for statistics, data, machine learning, R is very good. The community thing comes with the price. A lot of people are creating stuff, and there are no like actual good practices. There are 10 ways very often that you can achieve the same exact thing. Of course, there are 10 ways like in the algorithmic sense, but I'm talking about syntactic sense. Sometimes just people wrote something, and you can achieve exactly the same thing with the same complexity, just write it differently. If you want to start working with R, it's very easy. You're downloading R, it's small, it installs almost instantly, and then you need an IDE. The most popular IDE for R is RStudio, which if you look at it, it looks like something from 90s, but it's still the most popular. And those slides, I will publish them, so don't worry about this. I have two GitHub repositories. One is the code that I will be showing you exactly, and another is the workshop, the tutorial you could also look at. And it has the whole list of all of the packages. Supervised machine learning process is the process that starts with data. Well, surprise, surprise. Then you need to clean this data, pre-process it, and split the data. I've put only small squares, but if you've done anything with machine learning, you know cleaning and pre-processing, preparing data can take up to 90% of your time. So there is no good machine learning talk about without complaining about data pre-processing, so you have to do it. The fun part is actually this big square. There's no reason why I made it big, I just like it, and I think this is the cool part. But you need to do all of this. So we're splitting the data on our training and testing set. Why do we do it? Because algorithms has the tendency to overfit, which means learning the data by heart. So they can go fitted very well to the data they learn on, but when the new data comes in, they're lost. So that's why you should split your data and check performance of your algorithm on the data it hasn't seen during the training part. Once you have your model, as I told you, once you have your trained model, you could use it to score new example to evaluate your algorithm. So I will show you how to classify handwritten digits in R, and it will only take, the code will only take one screen. But of course, like with any programming language, one screen of code, 5 lines or 10 lines, very often takes you much more thinking about it, preparing it, etc., etc. But because of this particular problem, I found this dataset that is already prepared, cleaned, and I don't have to do much. So what they did is, let let's do it. What they did, they have 32 by 32 pixeled images. I've just noticed I cannot count. 32 by 32, they squeezed it to 8 by 8. It should be 64, not 16. And this will be the input of my algorithm. So instead of feature 1 and feature 2, as we had on one of the first slides, we will have 64 features. And those features will be numbers. Numbers representing if there is a black, white, or grayscale thing. And you can see this data set. It's publicly available, so it's very well-known data set. So what you could use, I'm looking at time, what you could use to do it is, for example, key nearest neighbor algorithm. This is the algorithm that is like the first one when you're learning how to classify stuff. And it's very easy to learn, very intuitive. So I have this green dot that I don't know its color yet. I found 5 nearest neighbors of this dot. Most of them are blue, so I'm concluding my dot is also blue. And you can see that this algorithm is, for example, better if you don't have a clear line between the classes. This could be used. The problem with this algorithm is every time you have a new dot, a new example, you have to calculate the distance to every other dot in your data set. And those are just dots, so like 2 dimensions. Imagine you have much more dimensions, much more data. Another example is using like naive Bayes classifier. I won't go into mathematics, but like every time I learn how naive Bayes classifier works, I have to go and learn it again and again before before I explain it to somebody else. The great thing with R is, and also occurs, I think, so you don't actually have to know how it works because you get the function and you could just use it. But I warn you from like using machine learning as a black box because very often those algorithms have some conditions that the data have to fill, and if you don't, you will get some answer, but you don't know if you can rely on this answer. So let's go to logistic regression. This is actually the line. This is the algorithm that will find you a line, assuming there is a line. And this is a slide I used to scare my boyfriend. He's sitting right there, pretending he doesn't hear me. This is a very simple math. If you're scared of maths and you want to go into machine learning, I would say don't be. Learn maths. You're a programmer, you're a technical person, you can do it. And this isn't actually a very complex one. This is how you evaluate your classification algorithm. So you have like accuracy, how many times you are right, for how many times for how many data there are. But there are also other metrics that could be much more useful for you. For example, if your classes are not balanced. Imagine you're trying to classify if somebody has breast cancer. Only 2%, let's say only 2% of people have breast cancer. If your algorithm is rubbish and only predicts you don't have cancer, it will have 98% accuracy. So accuracy is not always the great, well, usually it's not the greatest metric there is. So this is the code I've promised. This is a code in R that is classifying handwritten digits. First 2 lines, I read the digits from the files which were prepared luckily by the website. Then what I do, I'm saying my 65th column is an actual class I will be predicting. So this is reading, this is transforming my data, saying this will be a category. Factor is a function that's saying this is the label, this is a category, because you have 0, 1, 2, 3, 4, 5, 6, 7, and 9 classes, and those are labels, and the algorithm can treat them as numbers, and we don't want that. Then I use the library that is called caret, and I use k-nearest neighbor algorithm. And what I'm saying is, predict the 65th column based on any other column. The dot means the rest that wasn't already used. Use my training set, right? And use 5 nearest neighbors in this algorithm. And there you go, I have my model. After like clicking on this line, I have my model. It doesn't take even the time that I've noticed. What I can do with my model is I can now say, well, take my test set, the one that my algorithm didn't see during the training phase, and predict the labels. So this is my prediction. And what I can do with my predictions is I can compare them to the right answers because I have them. So what I'm doing is take my right answers, take my predictions, and build a confusion matrix. This took me much more code than I'm showing you here, but this confusion matrix function would display you all the information that I'm showing you here. I'm just bragging that I managed to do very nice visualization because R is also very good for visualization purposes. But this function will give you all of the numbers. So what we can see here, well, this algorithm worked pretty well. When it wasn't, this is the biggest error. So it's like it confused 1 with 8. Maybe someone just made a very thin 8 and it confused it. I'm never sure. Like another one is 9 with 7. So those are errors. Regression problem. Regression problem is the problem that has a statistical model, very well known. I don't know, maybe it's like 50 years old or even older. And like every statistician know them, and every statistician says one thing: this is a horrible model, but we still use it because it can be useful at some point. And the truth is, we don't have many regression problems that, regression solutions that can work better than ordinary linear regression. So ordinary linear regression is the solution, the model that finds the line that fits the data. And remember what I told you about the black boxes? You get the linear regression model, you get your data and say, find me the line. What it will find you? The line, even if the line is just not the right solution. Like let's say it finds you the line and it's kind of good. It's definitely not the straight line, it's a curve. Here, these data are not even linear, right? These data find a nice line, but actually it was skewed by this outlier. So look at your data, process your data, prepare your data, and go through a lot of preconditions that you have to do. Those are few metrics, a little bit more advanced maths, just a little bit, that is taking the true values, which are real numbers now, not categories, and takes the difference. And then takes the square root and divides it by number of examples. And then, like with classification, as human beings, we find it quite like normal that, well, we understand what accuracy is, how many times we were right. If you get somewhere a number from this, you can get a number like 1.7, or you can get 10,032. And if you don't know your scale, if you don't know your data, you may end up with the number that is completely gives you a number but doesn't give you any information. So there is a metric that only goes into the value of 1. So the closer to 1 it is, the better. It takes the average values and kind of like balances it. But still, even statisticians are arguing if this model is useful and if those metrics are giving you the right things. So I will show you how to do in R the regression model on Prestige dataset, which is a built-in dataset in R. So what we have here is education, income, percentage of women in the data. Prestige is like an index, so this is what we will be predicting. And then there is a census data, which is like a code, what's the occupational code, and the type. Is this a blue-collar, professional, or white-collar job? So I plotted the data to see them, and you can see like if women are actually influencing prestige. They're like all over the places. So I wouldn't say women don't matter, but women percentage in this data set probably doesn't matter for prestige recognition. And I did this quite easily. I just used the pairs function to just do this, and I'm saying like predict, use pairs and just don't include fifth and sixth column. I just didn't want to use census and type in here. The colors, you may not see it clearly, but they are like red, green, and black colors. They mean specific type. So I can conclude that probably education is linearly correlated with prestige from this. This is not linear, this is kind of a curve, but I probably could do something with it. And women don't matter, right? So what I can do, I can use LM function, which is here, and say predict me the prestige, take education, take logarithm from income, because it was a curve, so I wanted to make it a straight line, and take the woman. I actually took the woman here, but let's see what happens. And because it's a statistical model, it gives you all of the information that you can get from this model. Not just how good it is and all of the metrics, but also tells you which of those things that you've put here matter. And it gives you by starring it. So the more stars you have, the more significant this feature is. And it actually says women don't matter in this model. What you could do, I'll skip this, but those are a lot of preconditions that your data have to fill in. So don't use regression model if they don't fit in. How you can do it using the plot your fitting model, and it will give you all of the graphs. So how can I use type? Type is not a number, right? I cannot just plot it. When you have categorical data, you need to create dummy variables. But R is so kind. Dummy variables are just taking your categories and changing them into values 0s or 1. And this way, it just adds some variables to your model. But because of R, you don't have to do it. You're just saying, well, actually, take the type also into account. And what it does, it creates two dummy variables for you. You don't have to even think of it. But if you didn't know about this and just put type there, you wouldn't know what it is. And again, black box will give you some answers, but not necessarily answers you can interpret. Another thing you could do is to mix and match. So you can create new variables. But this is like much more hardcore statistics. A little twist, I used actually this to create the lines per type. So I actually fitted the lines, the regression model, but I spread it through the types. So this is how you could do it. If you know a little bit about statistics, you know what I'm saying. The last model, the last problem will be clustering problem. So clustering problem is unsupervised learning. And I see it all the time in tutorials. Like we have a clustering problem, which means gather the data together that are similar. And you can see different algorithms do it differently. So if you look at this, for me, this looks good and this looks good. This doesn't really. But again, I'm a human being and I look at this visually and I see circles. Machines don't see circles, right? They calculate something. In this case, they calculate the distance. So it gathered together the points that are near to each other. And I will show you how k-means algorithm works. Actually, the one that I didn't like. But it's the most popular and quite easy to understand. Once we have data points, we're saying cluster those data into two clusters. You need to say how many clusters you want. So it puts randomly two cluster centers and then calculates the distances to those centers and labels the data based on which center is closer. And then it calculates the new centers based on the data and does it again and again and again. And depending on what you're setting, you could like do it 1,000 times or do it until nothing changes really, right? So I will show you how to do clustering for Chicago crime data. And for me, it's really cool that you can do cool visualization with R or any tool that can do visualization, but very disappointing with clustering problem. But every time I talk about clustering problem, people want to see crime data because they are spatial data and you can plot them on the Google Maps. So this is what I'll do. And this data set is huge. If you go there, it's publicly available. They publish it every month. You can see how many data there are. I will just use the type of the crime and longitude and latitude, basically. So what I'm doing, I'm reading my crime data, and I'm using only assault and burglary types, because when I started to plot all of the data for just 1 month, my computer said, because there were so many. So I only take assault and burglary, and what I do, I'm using ggplot2 and ggmap. So first thing I'm doing is, I'm saying, take the mean of all of the longitude and latitudes and get the Google Maps. Get the map from Google Maps. So this is what this line is doing. This is a proper zoom. Took me like few minutes to actually do it in a proper scale. And what I am doing then, I'm saying on top of this map that I got here, print all of the points from assault and burglary. So this is just assault and burglary in Chicago. So what I wanted to do is I wanted to cluster the crimes by the space. And I use the function that is called k-means. I get my selected crimes and I only took longitude and latitude, and I wanted 6 clusters. Once I have this cluster result, I took my centers of my clusters and I took the, I just used the factor to use the colors, different colors for clusters, and I did exactly the same thing. I took the map that I created previously and I've put the points for my selected crimes, for my centers, and this is something that is connected with the legend. So these are my clusters. And I will tell you why it's disappointing. Because why would I need machine learning for that? Like, I had my points, so I could just say cluster 1, cluster 2, cluster 3, cluster 4. Clustering problem really is useful for like thinking of market targeting, but everyone wants to see it visualized. And I'm telling you, once you are visualizing your clusters, you really didn't need any machine learning. If you can do it as a human being, why would you write all this code? But this code will work for any data, for many dimensions, etc., etc., and as easily as I just did. But this way you could see it. So this is it. This is what I prepared for you. We went through machine learning workflow, machine learning process, and through the 3 classical machine learning tasks: classification, regression, and clustering. All the code is on GitHub, and also on Categorical platform will be soon. If you have any questions, if you have any remarks now or later, don't hesitate to contact me.